โอเคเริ่มใหม่แล้วกันแป๊บหนึ่งลูกขอจับ Okay ครับ welcome to the sixth class of Big Data Analytics. Today is a continuation from last Tuesday. Last Tuesday, if you will recall, we started on machine learning models. In particular, the paradigm we started with is unsupervised machine learning. Okay, if you will recall from the introductory class, I did mention that the three major paradigms of machine learning is unsupervised learning, sort of like analogous to what a baby does before he or she is taught formally by his or her mom how to name things, just observing things, putting things together, making random association, observing that appearance of mother is associated with, you know, warm milk and a nice feeling and so forth, right? And the second paradigm is supervised learning, and that's, you know, like when a baby learns from his or her mother exactly how to call an apple, and he makes a try, and if he does make the right call, then the mom say good. If makes a wrong call, the mom say bad. So it's an immediate feedback, direct feedback, and there's a ground truth. That's a word I want you to get used to. There's a ground truth to it. Whereas with unsupervised learning, there isn't necessarily a ground truth. Okay. If you recall last week, we played with simulated data. The reason I had you play with simulated data was because you created the ground truth. Okay. But in practice, nobody knows the ground truth, right? So that's what the essence of unsupervised learning. And then, of course, supervised learning is sort of like how you observe that certain types of behavior. If you're friendly to people, people like you. If you're not friendly, then people tend to stay away from you and so forth. It's kind of reinforcement positively and negatively. And that's under the rubric of reinforcement learning. That one is not going to be taught here. Because it's not as applicable to data analysis. Okay, it's quite applicable to control system, you know, like a programming robots or Roomba or whatever. Okay. Likewise, even with supervised learning and unsupervised learning, I put to you that this is just method that we are going to apply to data analysis, right? It's just actually one of the three, right? The three cornerstone of data analytics. One is visualization, in particular, interactive visualization, getting an insight just from looking at data in the right format, right visualization gives you an insight into how the data is organized. The second is probabilistic modeling or statistical inference, and that's something that you presumably have done already in year one of undergraduate. And so machine learning, you can think of as this kind of trying to do the similar kind of thing, but actually you end up being able to do more. And I want to say it's more and at the same time less. What I mean is that sometime in life, when the data comes with a certain intrinsic way of how data is generated, statistical model is actually better. Because with statistical model, you can make a lot more conclusion. You can make more detailed analysis, hypothesis testing, and all that. But the scope of application is limited to the data that really supports probabilistic modeling. For something more general, you definitely have to go to machine learning. Okay, but the discipline I want you guys to have is not to prefer automatically one tools over the other. Right? If I have a problem that is, you know, analyzing a set of data that's multinomially distributed, right? And you say, oh, I'm just going to use unsupervised learning. That's all nonsense. That's all nonsense. If there is a probabilistic underpinning to it, use probabilistic model. It's more powerful. You can do hypothesis testing, confidence interval, all kinds of stuff. Right? So don't prefer machine learning just because it's fancier or, you know, sexier this day. Okay. Having said that, again, we are going to spend a large part of this class with this kind of analysis, machine learning. Okay. Now, this is not a machine learning class, so the theoretical underlying may be glossed over at times, and I will give you more like a hand-waving intuition of how the data work. Okay, like last time, for example, if you remember last time, we talked about clustering analysis, right? Clustering, two major class of clustering analysis, right? One is distance-based, one is a density-based. Okay, so I gave you a sort of like a hand-waving explanation of how the algorithm work, and it's not far from the truth. For example, with k-means, what you do is you just hypothesize that there are 6 clusters, and you just randomly start with 6 center, okay, and see which data is close to it, and you assign to that center, and then you move center in response to the member of that cluster, and you keep doing this until it settles. Okay, whereas with density based, it's sort of like I ask you to hold hand the person that you can hold the hand to. Okay, if you can reach your hand and you can touch someone, touch that person, and keep doing this until the group is stopped. You can't reach anyone anymore, in which case the distance is a little bit too far out. Yeah. I owe you guys something last time because there's a question. I think it was a very good question. It looks like density based is much better, right? So why don't you use it for every cases? And so I think I owe you, I didn't give you a good explanation last time. So before I go on with today's coverage, which is mostly on dimensionality reduction, let me give you a good example of when and why you might prefer something else. Okay, let me draw this picture to you guys. Okay, let me draw this picture to you guys. Now, remember, okay, so remember that if data is kind of like organized around like a banana looking thing like this, right? Okay, then obviously it seems very obvious that this is one cluster, right? This is another cluster. Okay, and again, you can touch with short distance and so forth. So this seems like you would definitely prefer to use density based clustering. Okay, now let me give you another example. Same example, exact same example. What if, okay, what if the axis that you happen to draw this on, okay, is say client's wealth, okay, or say income or wealth, okay, and this is some kind of maybe asset value or something like that, okay, something like that. Now, in this case, imagine that I'm not trying to make cluster that has a very nice definition according to this this sense of the being contiguous or density based cluster. What if I want to assign 2 of my people 2 different jobs? One person is a sales that is very good with high wealth, high net worth individual, and the other person I would assign to sort of like a mass marketing, something like that. Okay, in which case it would actually make, you know, if I say did this with a k-means clustering, and I give it 2 clusters. Okay, I say I want 2 clusters. I want to do k-mean clustering. Chances are you can see that it's sort of like separate around this line versus this, right? So this guys would actually be part of this. So maybe I change the color. So maybe there'll be one cluster center here that covers this. Okay, whereas another cluster would cover this. Now these 2 guys, even though, you know, they are contiguous in some sense, and these are very contiguous, you can see that because this dimension has a real application implication, right? The application is I want to separate people really by kind of wealth. Okay, in which case that distance matter, this between big wealth and small wealth. You see what I mean? So maybe you end up with one cluster here and one cluster here. Okay. And I would assign two different groups, two different sales force. Okay. One force attack. So especially K-means, K-means is from a data scientist point of view. Okay. From a data scientist point of view, I don't like K-means that much. For one thing, it requires me to specify ahead of time how many cluster. Okay. Now that could be gotten around by trying a few of them. Okay. And there's elbow method, and we can actually go into that a little bit more later. But the point is, from a point of view of data scientists, it's not all that natural. It's like you're forcing it a little bit. But in practice, you do want to force, right? I have 6 teams, so I'm going to assign 6 cluster, right? No, not 7, not 5, not 3, not 9, even though that may lead to a very good data centric criteria. I just happen to have 5 people working for me. So I want 5 cluster, period. And I want to organize around wealth. So that would be how I organize my sales force. Okay. So this is where data science becomes a little bit of art. There's an art of applying different criteria. Okay. Doesn't mean that you're not doing anything that's not rigorous. You're doing everything rigorous, right? But the criteria changes. What's the criteria? Find something that is contiguous mass, or the criteria is, well, I want to separate people by wealth. That's my idea, because, say mass marketing or wealth client have to be treated differently. Let's say something like that. Okay. So that's one example. So when the axis that you are working with has a real world meaning, sometimes, K means some very, which to me it seems a little bit brutal. It's actually a better method. Okay. It's more congruous to how you want to use it. Okay. So, okay, let me go on. Okay. Now, I need to draw more pictures. So I said, in a sweeping statement, that roughly speaking, unsupervised learning comes in 2 flavors, right? So machine learning into unsupervised, supervised, reinforcement. Forget reinforcement learning. We're going to cover unsupervised and supervised. Within unsupervised, there are 2 types of analysis we tend to do. One is cluster analysis. Again, just, what we alluded to just now, how do entities clump up together in a high dimensional space. Okay. In 2 dimensions, you can do it by your eye view, right? Well, if I state that, let me restate that. Cluster analysis, why do we need a computer? Because it's done in high dimension. If it's in low dimension, do you need a computer to do it? No, you don't. You just plot, right? And this is where interactive visualization comes into play. In fact, all the example that I draw online is hypothetical, because I'm representing the problem in 2D, where in fact you would only use this if it's in high dimensional, 12 dimensions. Okay. The problem that I was just doing on Mondays, for example, 12 dimensions. Right. So let's focus on that statement. You would not need cluster analysis to be done by a computer if the dimension is 2. Okay. So that begs the question, is there any way we can cheat? Is there any way we can make high dimensional data low dimensional one? Okay. Then we can do clustering. Now, it turns out that approach is not great. And I'll show you, I think in the second half of the class, why that's not great. But hopefully that gets you thinking, it would be powerful if we can reduce the dimension. Okay. So first, again, it's not a machine learning class. So I do what looks like hand waving, but besides not giving you the mathematical notation, it is pretty much accurate. Okay. First of all, dimensionality reduction. I'm not gonna. Yeah. Dimensionality reduction. Dimensionality What do you mean by dimensionality? Yep. Close. Very good. Very good. Yeah, it is number of variable, but it's number of variable because you have as many number of variable as you have degree of freedom. That's what I'm looking for. Okay, this is not a technical students T distribution degree of freedom, but you can think of similar idea. Okay, you have 2 degree of freedom right now because you're standing on Earth. You can't fly. Okay, regardless of what the space is, you have 2 degree of freedom. That's you. Okay, a bird has 3. Okay, right. So the dimensionality gives you independent degree of freedom. Okay, it doesn't mean your movement is independent. Okay, because you certainly can't move 1 step in X direction and 1,000 steps in Y direction. Okay, you kind of, sometimes you can, sometimes you can't, whatever. The point is, what's independent is the space itself, right? It's organized around this 2 degree of freedom, 3 degree of freedom. Well, let's go back to, so dimensionality is a structure of the space. What do you mean by space? Space is where you can have things, right? Right? When you have space, big space means you can put more things. Small room means you can't pack that many people. Big room, you can pack a lot of people. Why do you say that? Because the distance between objects in the space matters. Distance. Okay? So relating what I'm going to talk about today, last class, where we talk about, distance-based clustering. Okay, so we're going to focus quite a bit on distance, Now, what does distance do? What does distance do? Distance is a measurement. It's a measurement that doesn't take 1 object. It takes 2 objects. If I take a height of a person, okay, how many variables do I take? How many arguments do I have? 1 person. If I take a distance, can I take this distance as a function of one thing? No, you always have 2 things, A and B, right? Now, occasionally, well, not occasionally, by default, you assume A is like 0, 0. So I can say that your distance from ground 0 is 5 meters, but actually you have to have a reference point. So it's always 2. It's always 2 things. It's always 2 things, right? So space allows you to put things, okay? And you can put more things if there are more space. What's the limiting factor? You can't sit on top of one another, right? So if A is not B, distance between A and B must not be 0. Okay? This is, again, this is not a technical machine learning class, but, with a more technical definition, I have to use the word like metric or something like that, or a metric space, but this is good enough. This is good enough for the purpose of this class. As long as you can measure a distance in the dimension of the space, you're good. You're good. You can do all kind of data analysis, and that's good. All the mathematics, well, not all the mathematics, but at least for the first class of this course, that's all you need, right? So if A is not B, the distance must be greater than 0. Okay, that's what I mean by space. That's it. That's all the space needs to be. Now let's go back to what I talk about. The subject today, dimensionality reduction. If the dimensionality describes the architecture or the structure of the space, dimensionality reduction, okay, if I reduce from dimension n to dimension m, that also implies that I'm going to a different space. Okay, so dimensionality reduction is a map. It's a map of where you are in one space to the other space. But the word is reduction, not enhancement. So you always go to more dimensional or less dimensional. Less, right? That's what you want. I mean, that's obviously, right? How much less? Now, this is where it gets tricky. It's very important. A lot of people understand that dimensionality reduction is to get everything down to 2 dimensions or 3 dimensions so you can understand it. That's not it. Okay, that's a very preliminary. Okay, you reduce high dimension to 2 dimension to 3 dimension because your brain works best in 2 dimension and 3 dimension. Okay, now I'm going to give the way at the end of the game. There are in data science problems where you have n is equal to 1,000 dimension, right? But the best thing is to reduce that n equal to 1,000 dimension into m is equal to 55 dimension. You still can't see it. But what can see it? A machine learning algorithm. So it's not to 2 to 3, just so you can see. It's to something lower that a machine can see. Okay. Now, what I'm going to say is a little bit subtle, but I have to say it because, you know, it's the right point to say it, but you can forget it as soon as I said it. Computer doesn't care if it's looking at 55 dimension or 10,000 dimension. So you're not actually helping the computer because the computer has a limitation. With human being, you have to reduce it 2 to 3 because we have that limitation. So when I say it's best to reduce 10,000 dimension into 55 dimension for the computer, it's not because the computer is going to complain. It's because there's something inherently definite about that data set that uses just 55 dimension to separate them. Okay. In other words, okay. Now this is very subtle. Think, okay. You guys live in 2 dimension. No, you live in 3 dimension, but you actually are organized in 2 dimension. So do I need 3 dimension to separate you guys? Do I? No, absolutely not. So this is exactly what's happening with dimensionality reduction. The space is 3 dimension, but I only need to know your information in 2 dimension to separate you into cluster. Okay. So 3 is too much, superfluous. 2 is just right because with 2 dimension, I can say that's one cluster. This is one cluster. Now, is 1 dimension good? No. 1 dimension is not good because I can't separate you two. Okay. So 3 is too much. Now I want you to remember this. 3 dimension is too much to separate you guys. 1 is too little. 2 is just right. Okay. Dimensionality reduction in data science, it's because in real life, the data is in 3 dimension, but it separates in a plane. So 2 is enough. Restaurant. Yeah. Okay. So you can have, yeah, definitely, because you can sit on the same table, right? There's a little bit of space. Yeah, that's very good. That's very good. So you obviously can sit in the same space, just, okay. So anytime the limitation, the idea here is that 3 is too much. 2 is just right to separate you guys. Now, if I were to have a machine that cluster you guys, okay? Now watch this. That machine is not a human being. It's an algorithm. Is it going to have a pre-installed inside that human being can fly? It doesn't, right? So it's going to search separation in the vertical too. It's going to waste a lot of time. Okay? It's going to waste a lot of time. And in fact, it may create a separation that makes no sense. Okay? So the reason we reduce dimension from 3 to 2 is so that when the computer machine learning algorithm works on it, it extracts the right amount of information, nothing superfluous, and doesn't throw anything away. Okay. So in this class, you will primarily, because you're not data scientists and this is not data science class, primarily you would think of dimensionality reduction as a way to compress everything down to 2 to 3 dimensions so you can think about it. because you're a human being. You just like that, okay? But I want you to know that in real life, data scientists, that is not the optimal condition. Optimal condition is go down to enough dimension to separate the data. Okay? Now, is that easy? No, absolutely not. Okay? There's a lot of experimentation involved because nobody knows, right? Right now, we are omniscient. We know, I know where you guys are. So I can say the 2-dimension is good. But I'm looking at data that's in 10 dimension, 50 dimension, 100 dimension. How do I know that 75 is good? Nobody does. Nobody does. Okay, there's some heuristic and blah, blah, blah. And sometimes if you reduce it to 10 dimension, you feed it to a neural network that does prediction. It does prediction better than if you didn't reduce it. Something like that. Okay. So you do some kind of grid search. There's 100 dimension, reduce it to 50. Make a prediction, see if you did any good. Reduce it to 20, see if it makes any good. Well, they're both bad, but 30 is about right. So pay. Okay. So there's a lot of fudging there. Yeah. Yes. Experiment. And that's the underlying science in data science. I can tell you all the theory that there's an optimal dimension between 1 and 3. And this in case is 2. I can tell you there's an optimal dimensionally between 1 and 1,000. I have no idea what it is. You can only find it by experiment. So it's an empirical science in a way. Okay. So it's not just empirical data. The science itself is empirical because the parameter itself is empirical. That's by the way, it's a very subtle point. Most people, even professional data scientists, haven't a clue. I've been told I need to do this every few minutes. So you can help remind me. Right. So this is the name of the game. Now, hold on. Where are we? Okay. So what I want to do in dimensionality reduction is if this is the same, I want to do exactly like this. But instead of doing it in 3 dimension, can I do it in 2 dimension? So I move this guy from 3 dimension to 2 dimension, 3 dimension to 2 dimension, and so forth, right? That's the name of the game. Now, this criteria is not enough. This criteria means you can't step on each other's toe. There's another criteria. Again, this is actually all mathematics, but what you would hope, okay, what you would hope is that if you now have 3 things, okay, and this is in dimension, original dimension, could be 1,000, okay, I'm going to use just nothing and then R for reduce, okay. So what I hope is this. I'm going to move these guys down to A, reduce dimension, move this guy down to B, remove the dimension, move the guy down to C, remove dimension, right? Now, what did I just erase from the board? I said, if these 2 are not the same, then these 2 cannot step on top of each other, okay? But that's not good enough. That's not good enough. I want to keep something like this. If this distance, okay, and this distance, okay, which one is bigger? I literally just make it like to look like A and B are closer to each other. Okay, so this guy is smaller than that guy, right? That's what I want. I want this relationship to come down as well. So this is kind of like technical word would be topology preservation or all kind of, but what it means is that if you close in original space, you close in original space. If you are far apart, if you were enemies in the high dimensional space, you're not going to be friends in lower dimensional space. Okay, so friends are friends, foes are foes, doesn't matter which dimension. Okay, now that makes life a little bit difficult because now you too, actually, if I say just everybody walks to the front, you will have the same distance. Well, the other that guy behind you will actually be on top of you. That's no good, right? So that definitely is not good. The other thing that's not good is the distance, right? the distance. If you put everybody here close together, you and the person behind there is actually far apart, but ended up being the same distance as this guy. That's not good. So this distance is small, that distance is big. If I compress you in one dimension, I want to do the same thing. Okay, that's what this means. Okay, so what's the goal of dimensionality reduction? Is the map a representation of data points in n-dimensional space, in m-dimensional space, where m is less than n. Okay, strictly less than. Okay, such that you maintain identity. So you're not the same person, you're not the same person. And you maintain, for this class, we'll just use the word affinity for closeness in it. Okay, so you keep affinity. Now, is it 1-to-1? No, that's too much. Okay, I can do this. I can require that. If you're twice as far in 3-dimensional space, you're also twice as far in 1-dimensional space. It turns out if I did that, you'll never get anywhere. Okay, you won't be able to solve it for everyone. Maybe you can take just two. There's no general function that keeps all this very nice proportion and distance. It's very hard. Let's put it this way. All you hope is that less and more. Okay, but if you're gonna say like it's twice as, you know, then you have to go into some kind of linear assumption. That's very difficult. Okay, there's a whole class of mathematics dealing with things like affine transformation and whatnot. Definitely, we can't say anymore. I will not be able to say anymore about what happened after the data is compressed. Rather than that, if you're not the same guy, you're not the same guy. If you're close, you stay close. If you're far, you stay far. Relatively. Okay, that's all I can say. That's all I can say. Okay. How about this? How about I'm going to not look at distribution of you two in 2 dimensions. I'm going to look at your distribution in 3 dimensions and have everybody stand up and take the head, just the head, just the head. Okay. Now you actually distributed in 3 dimensions, right? Right. But in a way, because you guys are not friendly to people of the same height, and the height is not that different, right? Does it matter much? So you can imagine that there's another problem in dimensionality reduction. You're not exactly reducing dimension, but you are trying to identify which dimension has the greatest separation. So in this case, left to right has the greatest separation. Front to back has a second separation, second most significant. The height of your head is tiny, the variation. So in this case, is it dimensionality reduction? No, it's still 3 dimensions. But by saying that left to right is the most important component, I identify the axis that is the most relevant. Okay, except that axis is not necessarily orthogonal, like front left, left right, but it might be something like this axis. And that's also a problem in dimensionality reduction called principal component. We're going to do both. Okay. Okay. Yeah. I don't need you to be able to write down the mathematics, but this condition that I mentioned, why do you do dimensionality reduction? These are all things I want you to know, and things you can certainly expect on the midterm, and that's 2 weeks time. Okay. So let me erase this. Okay, so we did cluster analysis. By the way, I have more example. You can cluster colors and whatnot, but I didn't use that class. Let's see, we did this, right? We generated the data set and blah, 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 all kind of stuff and fun things. And we encapsulate everything in the, actually, let me just quick, yeah. Okay. Now, let me collapse this. By the way, I just want to tell you that I'm playing with different method of clustering. This one is called k-means, obviously. It has like I had to specify or whatever, or no, actually this one is Gaussian mixture. This is neighborhood contraction, contracts everything into one space. Okay, now. And okay, I'm going to copy this and give it to you in the line group, right? Okay, so I'm going to call this, sorry, I use Sigma. Now I'm going to make it S1 and S2 just so that it's not so difficult to copy, right? Okay, what does this function do? What does this function do? I'm just going to list plot, right? I'm listing plot, list plot it, right? Random variate. So I randomize how many data point? 5,000 data point. Using what? Using binomial distribution. Now, binomial distribution, if you recall, go F1, it asks you to specify the mean, the standard deviation, and the correlation. Okay. In this case, I happen to not care about the location. So I give it 0 and 0. Okay. And what I care is that standard deviation are different. So one axis is more spread than the other. So S1, so that's X. S2, that's Y. So you can see that this has what? 4 times as big standard deviation. Okay. So binomial distribution, center around 0, standard deviation 0.8 and standard deviation of 0.2. Right. And correlation, no correlation. So completely independent. So you will get this kind of oval lines. Actually, it's elliptical. Yeah, elliptical. 500 of them. Oh, 500,000 of them. Now, I plot the range again because the X is a little bit spread out. So I plot from -3 to +3, and Y I plot from -1 to +1. Right now, if I didn't put aspect ratio, what's going to happen is, again, this Mathematica is a high level language. It makes a lot of assumption about what you want to do. So if I didn't do this, it just assume you want a square picture. Okay, which squarish picture. This is kind of standard. So I want to emphasize that, yeah, it's 3 to 1. So I put this. So that's okay. That's kind of like window dressing. Okay, but that's okay. Right, fine. Now, this thing I'm going to call cigar shape. I'm going to call it cigar shape distribution. Okay. It's basically normal distribution. Right. Now, if this were okay, if this were a distribution of people, again, what's the dimension? 2. Correct? 2 dimension. Okay. Now, the problem I'm going to talk about now is principal component, which means that I'm not going to right away reduce from 2 dimension to 1. Not yet. That's not my job today. Not right now. I'm going to start to have 2 dimension, but I want to identify which dimension has the greatest separation, right? So this will be analogous to left to right and front to back for you guys in this room. Okay, exactly the same. Okay, so except you guys are not in a cigar shape, but let's say it's in a cigar shape. But that's obvious, right? If you see this, okay, if you see this, what's the most important axis? X or Y? Anybody? X, right? X is more important than Y, okay? Because X has higher separation. Now I'm going to make life a little bit more difficult. Okay. So now, instead of having the original dimension, I'm going to twist this thing around. Again, I can use the real data, but you guys forgot trigonometry in high school or not? If you haven't forgotten, this is what's called a rotation matrix, cosine of theta and minus sine theta and sine theta. Do you guys remember this or no? No? Okay. Well, if I have a point, here, right? Say something like 5 and 1. Okay. 5 and 1, right? And I want this point, I want to rotate it, say 127 degree. Okay. And you should know this if you like gaming, because that's all you do, by the way. How do I rotate 5 and 1 into, say, minus 4.7 and 1.8 or something like that? How do you do that? You multiply by the matrix of cosine theta minus sine theta, cosine theta, where theta is 127 degree, except this is expressed in lambda. So you multiply this by 5 and 1, and you will get a new number, which is something like minus 4.7 and 1.3 or whatever. Okay. This is called rotation matrix. Okay. This is called rotation matrix. Okay. Let me start the line group and I can send you this thing. So this would be where are you guys? Yeah, take a while. So right. So this here, I'm plotting original set. I'm plotting a second set. Now I happen to do this. Okay. So now I can make this manipulate, obviously. Okay. So I can play around with the theta. So I can move it. Notice that if theta is exactly equal to pi, that's 180 degree, right? So it's the same thing as before. If your 50 guy is 180 degrees, like right to left, left to right. Fine, that's boring. So something more interesting like this. So this is the angle of rotation. Okay. Now, what I really want is to play with this guy. I want to play with this guy. Okay. By the way, I can, make it fancier, and instead of histogram, I can, yeah. So instead of just list plot, I can okay. Now, okay. So this is sort of like the final shot. Okay. I'm going to do a little bit of hand waving here, but okay. Oops, sorry. Principal components. Okay. This is the function that I'm going to use. Now, mathematically, what does it do? Oops. Let's go to this guy here. And this is where matrix, if you know matrix theory quite a bit, essentially I'm going to be doing a projection. But if not, then never mind. Okay. So this is what I'm doing. Okay, watch. This principal component analysis, okay, it does some calculation, and I'll go over the detail, but the end result, okay, is that it gives you 2 lines. Okay, 2 lines. It's 1 line. Okay, and let's change another color to green. And this is another line. You guys see that? Maybe I make it red. Guys see that? Right? So this original cigar is rotated. Now I know the rotation angle, but in life you don't know because you didn't create this data. And you don't even get to look at it because it's actually in 20 dimension. Okay. In 20 dimension, this function, principal component, will give you 12 lines of various length, roughly speaking. Actually, what it does, it gives you 12 line and then multiply it for the length. But okay, so let's just say that it gives you 12 line of different length. Likewise, here is 2 dimension. I give you 2 line of 2 different length. Obviously, which one is longer? Red or orange? Red, right? Why is the red longer? Because it aligns itself with the disc along the axis of greatest separation between data point. Okay, again, today we really focus on distance, guys. We really care about distance. Okay, we don't care about the individual data point, just distance in the space. But this distance is dictated by the occupation of points. So just as if I have this line, it's the greatest separation, but for some reason I rotated you in angle theta. Okay, I want to do the same thing. Obviously, that line is no longer going to be parallel or orthogonal to the room, right? So that's the line I want to get. Now look at the 1 point. Now look at my hand. 1 point. Let's say this point. Color green. Okay, this color. Okay, I'm going to make what's called projection. Projection. Okay, basically, this has some kind of unit. This has some kind of unit. So this is like, so let me mark the unit of the. Okay, so let's say 1, 2, 3. Okay, let's make it 1, 2, 3. And in yellow, okay, I'm gonna make it 1. And so here it's also 1, 2, 3. Okay, so here it's 4, 5, 6. So if I read the number on the screen, I should have made this bigger, shouldn't I? You guys want me to make it bigger? Yeah, I can do that. Take a second. Where am I? Yeah, so to plot this, I'm just gonna say plot. And I make it image size large. Okay, let's do that. And likewise, let's do this. Okay, and I make it very large. Okay, and I don't want to use this. I want to look at the list plot. Let's look at the list plot. Let's go back. Now it's huge. Okay, excellent. Okay, it's big now. I have to make it small because again, for the textbook, you can't make everything that big. So let's say I have the first axis. This is my second axis. So, okay. So I'm going to make it front and back, right? 1, 2, 3, 4, and 1, 2, 3, 4, say. And I'm going to make it, oops. Hey. Okay. Okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now let's take a point. Let's take one guy. Where was this guy? Let's make it, say this guy. Okay. I'm going to make what's called projection. So that means I go straight to the river. Okay. This is the river. I go straight to the river. Okay. What's that number over there? 123.5. Remember that? First axis is 3.5. And I take another one here. 2. Okay. So in the original dimension, I am something like what? 2 and a bit and 5. So normal, originally I would be here, right? Something like 2.8, comma 5, comma 4. Okay. Now I don't have 2.8, comma 4 anymore. I have a new number, which is 3.5, comma 2. Okay. 3.5, comma 2. In other words, I'm no longer expressing original coordinate. I change the new coordinate, change everybody. So in reference, any point, by the way, in the original coordinate, you do the same thing, right? You run straight to the axis, same thing. If you want to know what the value is, you just run straight to the axis. Okay. And see what number it gives you. Okay. So this here, this one here, and here. That's it. Right? Originally, you get this number and that number. Now you get this number and that number. You get this number in X, you get this number in Y. Now you get this number in red, this number in yellow. Okay. So this new point now is 3.5 red and 2 yellow. Okay. And just, to make story short, that point now, new coordinate, red, yellow, red and yellow is now 3.5 and minus 2, right? So it's this point. So obviously now it's going to have the same scale because it's sort of bunch things up in the high, in the largest one. Well, these are called component, just a name. Okay, so component is like axis, but a new axis. And the one that has the most stretch is the principal. Now, principal just means big. Okay. So when you have big, you can have small. And any of you guys play classical music? You have first principle and second principle. Well, same thing here, right? In this case, you only have 2. So one's principle, the other one is not that important, okay? But in 10 dimension, you can say, well, this line is first principle, this line is second principle, this line is third principle. It's called principal component because now you can say this point is equal to 3.5 red plus or minus 2 yellow. So it's a component that when you add to the weight, give you the point. That's why it's called component, right? Component is like when you baking a cake, right? You say 5 ounces of this and 5 ounces of flour, 1.5 ounces of sugar. Okay, so it's 5, 1.5. Same thing here. Instead of flour and sugar, you have red and yellow. And red is more important. You call it first principal component, second principal component, third component. Now, have I reduced any dimension here? I have not. Okay, but if you run out of space, originally you have to write 2 numbers. Now, if I want to write one number, which number would I write? I would write 3.5 because that gives me the location in the biggest spread. So think of trying to find some guy, right? You're doing a search, okay? So tell me, I'm gonna go find my friend. Okay, tell me the first axis first. Go to the principal component. You walk 3.5 steps. That gets you as close as you are gonna get. Now, if I told you to go -2 steps in the orange direction, are you gonna get that close? Not that close. Not that close. So the first number is more important than the second number. In this sense, it is dimensionality reduction, because if you are forced to choose to represent location in a lower dimension, you can, because you prioritize. Okay. So what does that mean? What it means is that along this axis, if I compress you along this axis, you still have some degree of separation. If I compress you along that axis, everybody's going to be standing on each other's head, right? Right? So so that's why this is important principle. It's a principal component. That is a second principal component, because if I'm going to quote one location number that guarantees the greatest separation, I would do this. Okay, that's more important. Okay. Economics. In economics. That's a good time for a break. Let me just mention to you, by the way, and this is not data science, but this is one of the things where principal component is like, you see it every day. Okay. Let me just draw a picture and then we can go to a break. I try to be disciplined with my guys. Okay. So let's do this. Okay. This is what's called a yield curve. What it means is that, let's say 1, 2. If you go to a bank, okay, and you put your money in a bank for fixed deposit for 1 year, you get 3%. So 1 year gives you 3% per year. Now, they'd like to keep you around longer. So they say, you know, if you promise to put your money with me for a year, I'll give you 3%. But if you promise to stay for 2 years, I give you 3.25. Okay, per year. So you actually get more than 3.25, but basically that, right? So you have this point, and presumably that point. Now, this line doesn't have to be linear. In fact, it can go something funny. Okay, this is economics. This is life. Okay, so we can't make life work the way we want. So this is called a yield curve. It's a plot of rate of return for depositing for a fixed amount of time. Let's say, think of it that way. Now, the line here is not with what economists are worried about. They're worried about movement. Okay. Now, if I don't look at this, but I look at movement. So let's say tomorrow. You guys see that? What happened? Look at the screen, guys. Don't just talk to each other. Okay. What happened to the from red to yellow? Anybody? It moved up. Obvious. What else? Exactly. Steeper. Okay. What else? It used to be very curvy, right? Now it's kind of like less curvy. So 3 things happen. Shift up. Shift up. Slope up. What else? Curvature down. Okay. And there's some other movement. Okay. This is what we talk about by principal component of a yield curve. The most important thing in life will happen in this order. And this is not just, you know, a nice mathematical elegance. It's literally empirical fact. The biggest movement, principal component, is this guy. What's the second principal component? This guy. What's the third principal component? This guy. Now, it may be that from data set, this is not the case. But what happened is what they do is they decompose the movement, and they find out that the biggest movement is everybody goes up and down together. They call that a shift. The other movement that's also big is that the further out and the shorter you are, they kind of like inversely, you know, if it's big move over there, small move over here, or if it's big move over here, small move over there, that becomes slow. In market speak, it's called steepening. It's a silly word. It's steepening. Okay. Finally, the other movement is, well, the middle goes up, but the sort of like the far end and the near end go down, or the middle goes down and the far end and near end goes up. So that means that you're moving the curvature, right? In this case, it's positively, so it can actually, normally, by the way, it looks like this. Next, normally, okay, but you can have this, you know, depends, you know, sometimes you have what's called the yield curve even. Very famous, happened in Hungary, and this was way back when. Okay, it doesn't happen often, but in European economy, because of monetary condition, whatnot, you know, the Hungarian yield curve went upside down, so the slope was negative for a long time, I guess. I don't know how long. I didn't really study history, but that's the movement. So a lot of people your age who will be working for the Bank of Thailand, say, you know, from economic department or central bank, or maybe a commercial bank's economic desk, you are being paid. You are going to be paid to get this thing predicted. Okay, it's not that hard. So you get paid to do this thing too. It's also hard, but not that hard. So you get paid to do this as well. Okay. And you can actually make money against the market prediction. If you get this better than the market, you win. If you get this better than the market, you win. If you get this better than the market, you win. It turns out because of the leverage, even though this is a small point, you can magnify the effect, but that's financial engineering. You don't need to know that. Okay. So in this case, are there higher dimension? Perhaps, right? Maybe there's some kind of like fourth order movement, but 3 is enough. They would have some kind of rule of thumb, like this would explain 80% of the movement. This would explain 17% of the movement. This would explain 2 more percent. And the other 1% just noise. They don't bother. They don't bother anymore with fourth. So 3 principal component is good enough for a yield curve. And this is not just Thailand yield curve. It's everywhere, United States, America, fan brief, guild, all kind of stuff. Okay, follow this line. Actually, there's a reason why. But that's the principal component. So in this case, again, if you get the first thing right, shifting, you're good. That's the most important thing. So principal component is technically not a dimensionally reduction technique, but it's create new axis of dimension so that it prioritizes the dimension that has the greatest separation, followed by less so and less so and less so and less so and less so, until you get to the fourth component. You just call it noise. Okay, that's what happened in finance. But in data science, it's not always clear how many, but I regularly work with the first principle. I have not run across any application where I actually have to go to 2 principal component to get something meaningful. Okay, usually first principal component is just good. Once you get that, you're good. Okay, that's from it. Now Other people, like I said, the usage may vary, your mileage may vary, but from my experience, first component, boy, if you get that right. Okay, so have a break.